So ETABS is extended three-dimensional analysis of building systems. The focus is on design office and it is also used in research papers. Also in publications, you can find has been used. The reason is that it has such modeling and analysis features that would interest a design office as well as a research aspect. So a quick brief introduction on the usage. So it is basically a finite element analysis program that will be used for your building system analysis, structural analysis. So it is an integrated software package where you will be doing your modeling, your analysis, as well as the design. Design is also accompanied with the detailing that is also available in the latest version of this program, which is ETABS version 21. So in this session, we will be focusing on the modeling, analysis, and brief introduction to the design part. Now, how we are going to use this program, basically how we are going to interact with this program. So this program does not have a text editor through which you will have to create model. Rather, you will have a CAD-like environment where you can draw your structural objects to create your model, edit, assign, and perform analysis and get the results in graphical as well as tabular output. So it is 100% graphical user interface you're going to work with. So that leaves us with the memorizing of commands and keywords that are required to build. Secondly, we will be using object-based modeling technique rather than exact finite element. We will be defining objects and use them as is. Program will take care of the finite element meshing part, most situations. You will have the control, but program has its own default settings, which we will discuss as we proceed. So object based technique, modeling technique is nothing but we will be defining the objects such as a beam, a column, a brace, floor slab, a wall, anything as an object. We define them and we'll simply use them just to build the structure. Right? That's what object-based modeling. So when you open the ETABS program, whether it is 19 or 20 or 21, this is the beginning. And you will see this information when you're connected to the internet, like latest news, resources, and product release related information. And quickly you can access the new model and open existing model. You can start a new model from here, but typically it's a Windows-based program. You'll get a file menu through which you'll get these standard options and something related to the print, create report, recently opened files, etc. under this. You also get import and export option, which will be covered later. Let's start with a new model. So I will pick up a very simple model. Let the model be simple, but we will be covering most of the features that we'll be using for this model creation, analysis, and design. Right. So it is going to be a simple RCC building, a symmetric building we will take and proceed with that. So the very first form is called model initialization. Basically, we need to set the unit system in this. So in that we have three options. One is a default setting. In the install folder, there will be a model, and from that, a default setting will be created always. You can also create a model for that and begin from that setting. That's the first one. Second one is bringing in the settings from an existing model file. For example, you have multiple towers and one tower you have modeled, and the second tower will most likely you'll have the same settings such as loads, load patterns, load cases, load combinations, material properties, section properties. All of this can be one click and bring from the first model. And in the second model, you'll start modeling the tower in that. So that's the second option. Third option is completely starting from scratch, which we'll be using in this presentation. And we can set the display units. Going to keep metric SI, and you can see the items and labels that will be used. For metric SI, forces will be in kilonewton, moments will be in kilonewton meter, stresses will be in MPa, Newton per millimeter square, for convenient way of interacting with the parameters. You can modify this later, it's possible. The other settings, you can set it now. Typically, we know the design code that we are going to use. So steel and concrete, you can select, and you have access to these many codes. You are having international version. And press OK. Second stage is defining a grid system. So we are going to work in a 3D space. It's better to have a grid system so that you'll have the control over the model, as well as to get the views in a particular plane, plan, elevation, 3D, etc. So you'll have that benefit, as well as it will also be helpful to have grid system to create your models quickly. So you have to specify this in two locations. One is for the plan. In this model, the global axis, in this program, the global axis are labeled as X, Y, Z, and it follows right hand rule. You open your first three fingers, thumb is X, index is Y, and middle finger is Z. And the orientation is like this. When you look at a building from the top, then you'll get to see the X and Y, and Z will be along the height of the structure. So that's the orientation. We will see that in a while. So you have options to set a uniform grid spacing based on the model. You'll be specifying these. I'm going to have, let us say, this screen, and assuming that you're looking the model in a plan view, then your horizontal is X and vertical is Y. So number of grid lines in X. So this is X direction horizontally, and number of vertical lines in the X direction. You can specify. Similar in Y direction, and it's uniform spacing. You can do that. And typically, we'll be going for the custom grid or varying grid spacing. You can enter into this in here. You can see that information from the uniform. You can switch to spacing, 8-meter spacing, 4 and 4. I'm changing this 5, so just in case this is a varying span. You can see this getting updated in the plot itself quickly. And you can add more grid lines from here and specify. Let's keep it very simple. It is 3 span, 6 meters in X direction, and 5 meters in Y direction. Right. Then on the right side, you'll find the vertical or the story data. So in this program, each story, right, call that 100-story building or a 10-story building just by number of stacks of stories in the vertical direction. So the idealization here would be a set of floor slabs, say the floor in which we are sitting right now, and the floor beams and the columns or walls supporting this floor slab system below. This one set is called a story. Say we have 4 stories, typical story, and bottom story can specify. If it is uniform, obviously it will be different. Then you can go for custom story data where you can specify varying heights. Let's say story 1, we can call it as the architectural drawings. This, and you can change the height here. So ground to base is from the ground level to the foundation. That is also considered as a story here. You can also group some of these stories in case of high-rise towers. Then you can group some 10 to 15 stories in a similar framing. Then you can do that by making one of the story as master. And then the rest of the stories will follow that particular story. And you can group that way. It will be helpful in the modeling. But for now, we will limit to this definition. So you have this grid system and this story data. And then with that, you can actually pick up any of the templates such as a steel deck or a two-way slab system or a flat system based on the above information. Program can quickly create the model for you. So I'm skipping that template option. I'm entering into the grid only option where we'll be discussing various modeling techniques here. So grid only is the default. In case you selected any other, you can switch to this grid only option and press OK. This will take you to the working area where you can see 2 working windows. You can make any one active. One is showing a 3D view, the other one is showing a plan view. At roof level z equal to 12. So if you look at the 3D view, you can see the global axis, X, Y, and Z, and its orientation. Right. So this is a working window. You can switch to any window, make it active, and work in that window. There's one thing. You can have more windows if you want. Add new window. You can change the views. There are options. You can choose typically 1 or 2 would be sufficient. And on your left, you have a model explorer where you have quick access to various definitions such as properties, etc. Loads, load cases, etc. for quick access. However, for this presentation, I will not use this. This can be used later when you get getting confidence in your modeling and usage. You can switch to these shortcuts. I'd be using the primary way of accessing commands from the menu items. Right. So the interface, and you have draw, select commands on the left vertical pane, and then the top you have standard save options, etc. Zoom commands, view commands, assignments, analysis, and design shortcuts. So I will not be using any of these shortcuts. Let us discuss through the menu. And on your left bottom, you have information bar. Depending on the activity, you'll get some information here. And then on the right side, you can see the mouse coordinates as you move the mouse. Then you have control. By default, one story. That means whatever you do will happen in one story. If you have all stories or similar stories, effects will be replicated in other stories as well. For example, if you draw a beam with all stories, then all the stories will have in the same XY coordinates along the Z direction. Right. So depending on the situation, you can use this, but it is recommended to keep it one story, and you have other options to replicate to complete the model, which we will be using in this presentation also. And then you have a global view, viewport. You can have multiple grid systems. So currently we are having a simple grid system like this. You can also have a cylindrical grid system. Add this. So for example, the front portion of the building is having a curved layout. Then you can also define that, have it as a second grid system. You can switch to that grid system for users. And then lastly, you have the units. You have access to quickly set to defaults of that particular system you're working, or you can set it to consistent units, or you can modify individual item of the to any unit length. For example, length is in you can change this to meters, etc., inches, feet, etc. So it goes for all items. No change in that, but you have these options. One more thing about the units is it is dynamic. At any point of time, you can change the unit system, even after analysis and design, to get the output in the desired unit system. So the model will be saved in the first form where I set metric SI. So file will be saved in that unit system always. Right, that's about the interface. Now let's discuss the menu. And I would say rather the menus, this is the exact logic in which you are going to work or use this program. This is the workflow and exactly how the menus are also arranged. Leaving the first menu, which is a file menu, and then two menus such as the edit and view. Edit is for editing the objects that you have drawn, and view is to change the views. So leaving the first three, the fourth one, which is called define, is where we're going to begin our work. Remember, we talked about object-based modeling. So an object means it has its own properties, section dimensions, right? So imagine a beam, it will have a material property and sectional dimensions, etc. So that can be defined. Define that object. Other than that, you also define, the problem in hand, what are the loads that are going to act on the structure. So you will define various load patterns. And you also decide what kind of load cases you want, whether it's a simple linear static or advanced analysis such as dynamic analysis such as model or response spectrum analysis or time history analysis, a nonlinear static, a pushover analysis. All of this can be defined under the load cases and load combinations for various design use cases. We will discuss this in detail in a moment. Just let me complete the workflow or the logics in which the menu items are arranged. So that's the definition. So we define various definitions, and then we switch to draw. Draw means creating the model with various options. We'll create the model. And then we have select and then assign. We combinedly use these menus. For example, you want to select a beam and apply a load, a floor slab load, or change its properties, or applying it with different assignments, property related. Then all of them will happen with this. You'll select something and assign something. So you'll combinedly use this. So with that, your modeling assignments such as loads, properties, changes, or frame releases, numerous things that you can work with the modeling. We'll complete everything with this. Then we'll switch to the analysis. Analyze the structure and you get the results. So you get all under the display, various outputs such as deformation, force, shell stresses, etc. under the display. Finally, you have the design. So once you're convinced with your analysis results, or if there is a need to iterate the analysis with different properties, change in material, etc., any modification, changes to the structure, you run this, iterate this, and finalize the analysis results, and you can finally switch to the member design based on the material, steel, concrete frame design, so composite. You also get with the ultimate, the floor slab design, this program, and also shear wall design. So detailing I'm skipping for now. So this is the logic you're going to work, and exactly the menu items are arranged. So you can find your relevant or the command you're searching for in that logic. Right. So I hope this small presentation will help you to get the idea, and then in your practice sessions, you'll be able to do it. But in case any queries, we are here to help you. We will discuss it again in the next session. All right. Now let's continue this. I'm going to save this. Inside a folder. Saving on the desktop is not recommended. As you know, many supplementary files will be generated during the analysis. Better contained in a folder. Call this some name, and the file type is .edb. Right. So let's start with the definitions. First one, material properties. We'll see predefined materials. You can use them or even delete them if not needed. But these are defined in case you are using the templates. So program needs some definitions, so it is already there. Can define a new material using add new material, region based. So it is a RCC building, so a concrete. Let's say M25. It's a kind of helper which will take you to the actual material property data form. So this is completely editable, although you get it from our M25, you can modify this as you want. So isotropic material, M25, and you have the material weight and mass. And then mechanical properties. So this is 5000 and root FCK for IS code. Then you have this design property where you specify the FCK that will be used in the design calculations. So M25, it is 25. So there are advanced material property data such as nonlinear material data. So this will be discussed later. This is how this can be specified, such as material nonlinearity, time-dependent properties for shrinkage and creep, and in case of crack section analysis, so for the floors and beams, can specify the modulus of rupture. These are the definitions for this particular material. This is M25. We'll add one more, should be for reinforcement bars. This is called a rebar. Say 500. Similar definition, can have multiple definitions. Complete this. Next, we'll go to the section properties. So in section properties, for this example, we're going to define a beam, a column, a floor slab. Later, we will include the walls, frame sections. You can see various types. Section properties such as frames, tendons for PT slabs, slabs, decks, and wall sections. And we also have link properties for highly nonlinear devices such as dampers or isolators can define such properties using the link objects. We have the link object here. And for material nonlinearity, you have hinge definitions you can make available. Panel zone for steel structures. So these are the section properties. So we'll use frame sections to define a beam. So again, you will see the list of properties. For the same reason, we will create our own. So if it is a steel, then you can import properties from library. It's the first option. So this RCC, we will be defining the properties. So add new property. You have the various shapes, and select and proceed with the definition. And you can also get the frequently used shapes. For example, this is concrete rectangular section. I'm going to use this. And I will name it like this, be say 250 by 450. Idea is to have the section dimension in the name itself for easy identification, and you can specify the material. If you want, you can add the material name also in the text. Section dimensions, 450 depth and 250 width, and you'll see the plot gets updated for this specified dimension, and you get to see this axis 2 and 3. It is nothing but the local axis. So these are finite elements we are dealing with, so it will have their own local axis. So for a line element, which we are defining, again, it follows the right hand rule. You could open your first 3 fingers, thumb, index, and middle. It is labeled as 1, 2, and 3. 1 is thumb, 2 is index, 3 is middle. Right. So we are looking at the sectional face of the member. So the local one is always along the length of the line element, whether it is a beam, brace, or a column. So local one will be along the length of the member always. 2 and 3 you get to see in the sectional side. Right. So this, Local axes are important because your results will be in terms of local axis. So we should know the local axis orientation as well. Right. So this is sufficient for the analysis. However, we are interested in the design. So we will be specifying the reinforcement information in this, like this. Under reinforcement, you have the modify show rebar. And here you specify this line element is, should follow the design type column or beam. So beam, say longitudinal bars 500, confinement bars 4 on 5. And you'd be specifying the effective cover, which is the distance from the extreme concrete fiber to the rebar group centroid. Let's have 60 and 60. So this comes from experience. We're expecting a 2-layer of rebar based on size and depth, basically, how much it is allowed, and you decide on that and specify it from experience. So I'm assuming 2 layers, so approximately 60 mm from the extreme fiber for both top and bottom. That's all you have to do here. And for a beam definition, your rebars will not be displayed. Second, we'll define a column section. Add new property. Let's have a rectangular section again. This is C 300 by 500. It can be any material, but I'm going with M25 here again. It is 500 and 300. Note the local axis, which local axis 3, because when you draw an object, especially the column, the orientation is like this. The local 3 will be parallel to global y. Imagine I would draw a column here, vertical element. Its local 3 will be parallel to global y by default. You can rotate it later, but that's the default orientation. And also in the section dimensions, you can swap these values to have that particular orientation for this column section. If I draw this column, if you look at this from the top, you'll see a horizontally oriented column. You swap these values, then it will become a vertically oriented column. This is okay. Under the reinforcement, specify the design type as column, M2, M3, 500 for the longitudinal bars, reinforcement configuration, and you want this to be designed. You also get the option to check the capacity for the provided rebar inside a section. Then longitudinal bars, air cover for the confinement rebar, and number of bars along 3 direction face. 3 direction is this horizontal, so top and bottom, how many bars? And specify these values, and also specify the bar size. Confinement bar size, you specify it 8 or 10. So based on this information, program will configure the rebar layout and will be displayed this plot. This is important in the column design because program does not use SP16 PM interaction curves, but it will generate PMM interaction surface full 3D for the design. So this is explained in the design manual in detail, but obviously it is what used in the column design, generation of PMM interaction surface for various shapes. So SP16 is giving only for rectangular and circular section. What for other shapes, you will have to create them. So by default, the program always generates the PO interaction surface for any shape. So what we are using is a rectangular shape. You also have the option called SD section, uh, where you can create an irregular polygon as a column shape and specify the rebars. So program will generate PMM interaction surface based on compatibility method to generate the interaction surface and use it for the design. Right? And this will be more realistic what we're going to provide rather than simply uh, rebars distributed in 22 sides or equally on all 4 sides. Right. So that's the definition for a column. You can see the list gets populated, but you can also create a number of sections. Real problem, right? We'll keep this 2 sections for our model. Second one would be slab section, the floor slab. Add new property again. So we will call this S150. This S150, 150 mm thick, M25, and modeling type. You have shell, thin and thick, and membrane. And lastly, we also have layered or sandwich shell for nonlinear analysis. Specify various layers of rebars and concrete, and then that can be analyzed. Study the nonlinear behavior of the materials. So, but typically we would be using a membrane or shell. So we will use a membrane type for this, but I would give you a few examples when to use this. A membrane is a simplified shell that has only in plane stiffness. In plane deformations are possible. Out of plane, the bending is 0. So this can be used when the slabs are modeled only to transfer the loads to the supporting frames. So the deformations of the slab is not relevant for your analysis. Then you can use membrane. Deformations out of plane. So you can use shell, which will have both in plane and out of plane stiffnesses. For example, a flat slab system where slabs are resting directly on the columns. So the deflection of the slabs that are to be captured, and the distribution will also depend on that, and you have that with the shell option. Shell has all 6 degrees of freedom active. There's 3 translation and 3 rotations in each node. Membrane will have only 3 in plane translation and 1 rotation about the perpendicular axis of the plane. So within shell you have thin and thick. So when the thickness is very small for uh, members like floor slabs, walls, you can use thin and then thick. For example, a footing or a raft where the thickness is comparable to the lateral dimensions. You can use thick. So formulation is in the thin is excluding the shear deformations in thickness direction, and in thick it is considered. That's it. So these are all explained in the analysis reference manual, which is another important document that you should refer to. I will show them at the end. So for this case, I'm going to use membrane. which is a beam slab system. So slabs are resting on the beams. Can use membrane. In membrane, you also get one additional feature to distribute the load in one way. So loads are distributed in the only in the two edges, two opposite edges of the shell. So you have this option with the membrane. If you enable this, that is active. If you don't enable this, it will be a two-way distribution by default. And the type specify this. You have options such as solid slabs, which is slab. And you have drop for flat slab systems. You have stiff, which has a property, increased property value to model the junctions of, for example, a slab and a concrete column. You can use the other types for the slab and matter footing. So relevant only in detailing. Can leave it to slab and specify the thickness 150. So it's on 150 M25 thick slab of membrane type. That's what I'm using for this example. Right. So that's the definition, material and section properties. Now, there are other items which we will discuss as we proceed further. But for this example, we're going to specify the load patterns. So load patterns is to define various patterns of loads that are acting on the structure. And it will be also useful for the program to identify the type and apply respective load factors in the load combinations. So by default, you have dead and live. Can define a number of patterns as you need. For example, you want to define masonry loads separately, then you can create a load in the name of masonry and type. You can see various types. So typically it would be dead or live, the category, and within live you have reducible live for specifying, for considering the reducible live in the design. Roof live get ignored, the mass source, and you can also perform pattern live load analysis. And you have seismic and wind. We'll come to this. So let us have dead and live, two primary patterns of load. Then you'll see the dead is having a self-weight multiplier. That means whatever you model, by default, program will take care of its self-weight. Self-weight is coming from the material property definition, unit weight definition. So you can forget about the self-weight in general, but if you want to reduce it or completely ignore, then you can put 0 here and modify this. So self-weight will be ignored. So any other load pattern that you define here in the list will have a self-weight multiplier as 0, because self-weight multiplier or the self-weight should be considered only once in the analysis. All right, we'll come back to this for the lateral loads shortly. So we have only dead and live definitions. That's it for this first iteration. This is in design. And then we have load cases. So whenever you define a load pattern, program automatically creates a load case as a linear static for that. You can see in the same name. So load case is the actual case used in the analysis and for which you get the analysis results. So it is in the same name, so there will not be any confusion. So we have the live and dead as linear static. Just to show you what is inside this definition. So the name that it's a linear static, and you can see the various other types analysis cases: nonlinear static, staged construction, model, response spectrum, time history, etc. So this automatic load case definition will happen only for linear static, and it has p delta settings as of now. It is none, and applied load is from the load pattern dead. Scale factor is 1. So it also defines a model case, which can use it later. You can delete this if you want, or can keep it. It's okay. Then under the load combinations, where you can define the design load combinations as you need. Combination can be linear addition, envelope, etc. And you can add loads with factors. And these combinations can be included in your design load combinations, and it will be used. The other way to do it with the default combinations, yeah, you can do that. So based on the selected code, you can add default design combos. This is a concrete frame. Select concrete frame design and press OK. So combinations will be added. Even if you don't define these combinations here, when you click the design button, program automatically generates combinations based on the selected code. So any additional design combination you want to consider has to be defined here, and the same will be included in the design settings. All right, now keeping these two, that's the define menu. And these are the primary definitions that you make for any model, whether it is a simple model or a complex high-rise tower, etc. You'll be defining these things for each and every model, right? Other things we'll cover as we move forward, right? Using these definitions, now we're going to create the model. Now here, we are going to utilize the grid system that we have created. So you can see this 5 meter, 6 meter space spans. So just before the modeling, you can also quickly have a look at the view menu. Should be useful at this stage. See, you can see the options. So set 3D view, quick settings, or you can modify this. So decide view and set plan view. Plans can be selected using the names given in the story definition. Say ground floor, go to the ground floor like this, and view elevation. So elevation will be referred to the grid IDs like this. Want to see grid 2, select grid 2. Okay, can do this. With that, you also get, here's a shortcut here, the big up and down arrows here, which will simply scroll through the planes. Under the option, you have an option called show bounding plane, just to bring highlighting of this particular elevation. Elevation A, if you press one up, it goes to elevation B. Up and down, you can use like this. All right, so this shortcut would be very handy at times. So I'm going to model. So other commands you can experience by yourself: zoom, restore full view, etc. Zoom in, zoom out. Your mouse wheel is a zoom tool. The center mouse wheel button or the middle mouse button is a pan, similar to CAD environment. So under the view, I am switching back to a plan view at the ground floor, where I'm going to start the modeling. I'm going to use draw. You have options for the drawing, snap options, similar to CAD. You can enable this as needed. So currently it is joints and grid intersections. You can see grid intersections will be snapped. Line ends, midpoints, edges, etc. All you can use of. Right. Coming back to the draw, you have the three types: joint, line, and area. So in this program, uh, it is not required to create joints to create or draw the objects. So draw joint objects is rarely used when specific road application in the middle of a slab somewhere on the slab, then you can use a joint object to draw, or for some other editing purpose you can draw and use the draw to mesh the object, etc. Right, for those cases the draw objects will be useful. Typically you'll be using the line and area to create a model. You have the line element and the area element, but under that you have various options for particular type. For example, in this case, line, draw, beam, column, brace objects. In that I'm going to use quick draw columns. So whenever you find a quick, so it is going to make use of grid system. So I'm going to draw columns. I click, it will ask for which property to be used. Specify that we have defined. Then you have options within them to give a plan offset from the clicked point. What is the offset? The column has to be placed, the column has to be rotated, and it end moments are released or not. Currently it is continuous. And you can also specify the cardinal point, draw using the grids. So now you can see the vertical arrow, which represents the drawing mode. The regular arrow is not. As I move closer to a grid, you can see it snapped. And you click, and the column object will be created. You can also do this, creating a selection window partially or fully covering the grid system. So grid intersections. The program will also live highlight, and you can leave it to create columns in these locations. Similarly, you can go to quick draw beams option. This time it will be beam section. Again, you move closer to the grid, you can see highlight, click, create the beams quickly like this. Or you can also make a selection window between grid intersections. You can create. Then you also model the floor slab. There are various options. So first one is clicking multiple corners of the area object for any polygon shape. Second is for rectangle. Third one is for quick draw option, which I'm going to use now. That's 150. Although I'm selecting the property now, we can change it later. I'm going to use the grids. So as I move inside a grid between intersections, as possibility is shown, dotted lines on the edges, or you can also make a selection window. Complete this. I'm taking a bit time to show all of these, but can be done in very swiftly. So it is better to have a grid system ready for that. All right. In case you want to draw it manually, different locations, then you will use, for example, a line. First option is 2-point click to create a line object. You use this and you get options. Yes. So property, I'm using the same property here. I will use, can actually draw anywhere I want. You can see and start and create. And create lines like this. We'll be doing it in a certain way. So deleting the objects is very simple. You can select this object like in a CAD program. You have the selection window, same thing from left to right and also right to left. Make left to right, objects completely falling inside will get selected. Make the reverse, objects touching the selection window also get selected. And edit, say edit command, which is delete, or you can simply press delete on your keyboard to remove the objects. Select and delete. Right. Now, let us say we want to draw a beam somewhere here in the middle. Can make use of snap options, mid and line ends and midpoints. If I move closer to the object middle region, it will snap to the midpoint like in CAD. So you can now draw beam. And you can continue, and you can right click and start from a new location. Yes. Once it is done, you can press escape key or come back to the draw menu and press select object to come out of the drawing mode. So one more within the same command is plan offset, which I was talking about earlier. So you can specify from the clicked reference point how much is the offset. Let's say it is just 1 meter. It's asking in mm. So 1000 mm. And if I click here, you can see beam will be creating with that offset. I don't want this. Let's keep these secondary beams for a while and we will do some editing. I want to show you some editing tools under the edit. So under the edit, there are various options. Let's start with the move command. Select move. So let's say this beam, I want to move it by another 500 mm in the y direction. Then you can put 5, apply. Typical move command. So when you select a joint, then it will be interesting because when you move a joint, objects connected to the joint will also get stretched. Say if I stretch this by the x direction -1 meter, it can see that in the 3D view better. That's the move. And you have align command. Again, joints are powerful. So if I use any joint, you'll get and move, it will get stretched. Let's put back this in the same location, but this time instead of local delta dimension, we will be giving the exact coordinate. For example, this coordinate value is 18. We put align this joint to 18, it will be back to its original position. So you can align x, y, and y, z. And you can also align points to the near edges in case it is inclined one. So you also have trim and extend. For example, this beam, you want to extend this to till this beam, vertical beam. What you'll have to do is like this. You have to select this beam, and beam has the ends where joints are available. Select that joint and select the beam which represents till where the extension happens. Do this. Trim is reverse of it. Let's bring it back to the original. Select the beam that you want to trim and from which end and which beam is going to act as a cutting tool. This. These are the align commands. So merge is when joints are coming very really close. Some situations, and it can merge with some tolerances. That's what merges. Then you have extrude. Extrude joins two frames. For example, we want to create a projection from here. We don't have a grid system, or for some other reason, we want to create objects just from existing. So these joints, so I'm going to select in dx, say 2 meters, only in x, one time. It will create a beam like this. So extrusion works. It's linear, and you also have the radial. You can export those in your practice sessions. Then you have extrude frames to shells. For example, I want to create a slab with the help of this beam. Again, I'll project it by, let's say, 1.5 meter x direction, one time. And you also have under the draw itself one tool called reshape. You can also make use of this. You can select an object and you'll get handles to work with. For example, I can stretch the edge handles. Yes, or corner handles. Select the object, you'll get the handles again. Same goes for line. And under coming back to the edit, you have edit frames. For example, dividing a frame, and divide a frame into this many segments, right? Directly specifying number of segments, or you can select this beam and you want to divide this at this joint, and you can use intersection option. Now, if you select this, will become a separate frame this way. The other option is using the grid line itself as a dividing tool. Same goes for shells. divide shells, for example. Want to divide the shell, this beam, can use cookie cut option. This will be a separate object. This will be separate. Or you can use cookie cut with a joint, 0° apply, that will be a horizontal cut. Put, let's say 90. This should be on the edge. Say this object. Some angle, let's say 35, 60. You can see the cut. So the orientation for the angles, if you look at the, so this is the plan view, right? X, this is 0, anti-clockwise are positive. So 90 is Y, 180 is negative X, 270 is negative Y, 360. So you can specify like this, and you can divide objects into this many segments. For example, can divide this 2 by 2. This has to be rectangle. I use this area divided by 2 by 2 will get divided by like this, and divide with the help of selected joint where meshing has to happen, or intersection with selected frame object with visible grids. All of these options are available. There is an undo, like you can do this, and I don't want these things, select and deleting them. Let's divide, remove this one. Let's keep the secondary beams here only in these two locations. So for secondary beams that are resting on the primary beams, you typically want to have a shear connection, or the moments should not be transferred, right? The moments has to be released. Then you have option to specify releases, which I will show you. So this is under select and assign. Now we are switching from the draw to the select and assign. So in the select, we have various options to select and deselect to arrive at the final set of selection. So you can have this. For example, you can select based on the type, program will group objects as beams, columns, etc. If I select all the beams, you can see this. One go, or based on any particular properties, you want to select only that particular beam, then you can use any of these property definitions to, or directly with the help of labels. Now, what we are having with this select object, which is a default cursor, is you'll be able to select objects. If you select an object, it will get selected. Click it again, it will get deselected. Okay, that's how the selection works, and also the selection windows. These are the ways you can do. Being a simple model, I'm using mostly the mouse clicks to select objects like this. In a real complex model, you will be using all of these options. For example, selecting all the slabs in one go to assign loads. So even for this particular example, let's assign loads to these load slabs. Once the selection is done, you can see on the information bar left bottom, 9 shells and 36 edges selected. This is to assign. So first set related to join frame shell is for the property related assignments. And the second set is for the loads for quick access. This is shell loads. I'm going to the uniform. I'm going to assign the dead and live load using the load pattern. This is the key here. So you have to select pattern and apply what is the load. Let's say 1 kilonewton per meter square. Note the self weight is already included by default. So I'm applying only the additional load attached to it, such as floor finish, wall ceiling, etc. Then you can use this ducts attached to the ceiling, etc. You can calculate that and apply it as a uniform load. And the direction by default is gravity. That means the value should be positive and it is going to act in downward direction automatically. Or you can specify it directly in any particular direction. Let's have gravity, and you have the options how to apply that. And you want to delete it, then here is the option. Let's apply dead load of 1 kilonewton. It's got applied. I'm going to select the floors again. I can do this, or I can use select, get previous selection. Quick way to get back the entire set. Can even close this for now. And live load. Let's assign 2.5 kilonewton per meter square, the gravity direction. Apply. It's got assigned. Let's complete the loads. So masonry wall loads typically are assigned as loads. Then we can select objects, the beam objects quickly. Let's assume again the same option you can use and select all the beams. Let's assume only the periphery beams are having the masonry wall loads, interiors are not. Then how to do it? You can use this like this. So in this selection, you can also, you can see the columns also got selected like this. You want to exclude it, then quickly you can use the deselect option and object type and remove maybe the joints and columns together, leaving only the beams. And you can see in the left bottom 12 frames selected. So this, let's make this active and assign frame load. Can be a point load or distributed or temperature. Use distributed. Let's have all the masonry wall loads in the dead load pattern itself. You could have defined one more pattern for handling this. What happens is you'll get different various analysis results based on the definition. And you can combine them, even program can combine them together based on the type automatically. So it is up to you to decide on that. I'm keeping it with the dead, self weight and additional loads. So it is a force, can be a moment in the gravity direction, and the option is to replace existing. The trapezoidal load option and then uniform load. We will use uniform load. Let's say we have to calculate this based on the material thickness and other claddings, etc., associated with that wall. Can specify how much is the running meter load on this. Typically, what is done. The trapezoidal load is used to assign uniformly varying load, partial load acting on the beam. Those situations you can use trapezoidal. Let's go with the uniform. You can try the trapezoidal on your end and let me have these queries on that. Let's have uniform load, you can see. So keep the form open. If there are other loads acting on the structure with a different magnitude, then you can select those members like this and specify a new load to this. Apply. And finally, you can close this form. So this is how you apply the gravity loads. We'll come to the lateral load shortly in a moment. Before that, we want to discuss on this moment releases, certain things on the property assignments. So let's select this beam. I'll go to assign. So it is under the frame. You can find release from partial fixity. Here you can either release it completely. The default orientation for beams is like this. I will show you the graphical in a moment, but here the major moment about this plane, XZ plane, is M33. So I'll release end moment, this left end. Apply this, so moments will be released on this. So here I'm going to release only on the right end. If it is a single beam, then you can release both ends. So you apply this moment releases. There are certain other things such as under the frame, for example, end length offsets, insertion points. Right? End length offset is automatic from the connectivity based on the connection at this connected member dimension. Program will set the offset from the common joint here at the centroid to the face of the connected member by default. Right? If you want to specify on your own, then you can specify it by defining the lengths. You can have this connectivity. Right now it is automatic from connectivity, leaving it to that. Then under the frame, you have insertion points in case you want to specify a particular cardinal point where the member will get connected to the other member. These options. For beams, by default, it is going to be top center. That means the depth of the beam will be from the level where we model the line. It is like that. And for columns, it will be centroid. And by default, the stiffness will not be transformed, and you can enable this transformation here to have the effect in your analysis. Otherwise, only the offsets will be affecting with that without transformation, which is default. And you can also specify where exactly it has to be in terms of its local or global coordinate system. So we are not going to do this in this presentation, but these are the options you should know. We will see what is the default setting and we understand from that, and then we can modify it as per your needs. Right, now we have completed one story. So let's assume it's a typical floor on all other floors. So taking advantage of that, we are going to replicate this particular story, which is called ground floor. Single select or the entire story objects get selected. And this will be replicated. Replication is a powerful tool which replicates not only the geometry, it also replicates the properties and assignments to them. And the replication command is under the edit menu, edit, replicate is active. Then you have linear replication for laterally, radial and mirror, all are in the same story level. And you have a story separately in the vertical direction. The replication should happen at first floor, second floor and roof. If I go to the apply button, over the mouse on that, and it will highlight and show where will be the indicated objects. Press apply. That's how we can create the object. So locally at the roof level, there may not be this much high masonry wall loads, and you can reduce it in that particular level and then complete your modeling. Right. So one last thing that we do is the support condition just before the analysis. So if you would have noticed, you can see support restraint being assigned by the program automatically at the base level, just to avoid any unwanted errors without support condition. So it is a pin support assigned by the program. So I want to apply a fixed support condition to all the columns. How to assign that? Let me select. I can use various options. For example, I can use coordinate specification and use click joint in XY plane, or I can simply use the base story in the selection. So in this case, I will select a joint in this plane that will select all the objects in that plane. So at the base level, you have only the joints. You can see 16 joints selected. And let's go to the assign joint. You have the restraints. Here you can specify manually, or you can use the quick restraints: fixed, pinned, roller, no restraints. And we will apply this. Fixed is assigned. We are ready to run the analysis. One command, or not command, actually information that you can get from any object just by clicking on it is, the left mouse button is to select and deselect. If you right click on that object, it will bring this slab information or the object information in general, object ID, geometry, coordinates, assignments, what are the property related assignments, meshing assignments, etc., and load assignments, everything under one right click. For any object, even a joint, you'll get this restraints, loads, etc. Right? What are the connectivity to that joint? So it has only the column. You can see this. You can use this. All right, now we are all set to run the analysis. Then go to the run analysis and perform the analysis. But before that, we will have this set load cases to run. So you can see dead load, live load, and model. Here you can select only those cases you want to have in this run. I don't want the model for now. I'll select this and make it do not run. Then I can go ahead and run the analysis, or I'll close it for now. And by default, set active degrees of freedom. By default, it is a full 3D analysis. In case you're analyzing a particular frame, portal frame, then you can select only those degrees of freedom active for the analysis. Otherwise, there will be, if the degrees of freedom are not handled properly, then there will be errors. Very simple reason is that you're performing a portal frame analysis in a full 3D and restraints are not taken care of properly. Right? So you can select only those degrees of freedom active for the analysis. We'll come back to the full 3D default, and there are mesh settings. We'll come to that later, but for this, we will go with the default mesh settings, which I will discuss in a while. Let's start analysis first. Run analysis. So after the analysis, you can see the deformed shape of the window. You run the mouse over the joints, you can read the values or get the values like this in a form. What is the translation and rotation? And you can get a start animation, which would be helpful. So dead load deformation goes downwards in the gravity direction, but the animation reverses the sign and gets an animated view. This will be helpful to identify any connectivity issues in the model, and you can also understand the response is as expected or not. And you can attend to the issues accordingly. So animations will help you on that. So everything is under the display now. Display deformed shape. That's what we are looking at. You can change to any particular case or combo, see the results. Right now we are having only few combinations. And work with the various output options display. So we are at the deformed shape. At the deformed shape, just wanted to show you one thing about the meshing. You can see this is what we have modeled. Every floor there is a secondary beam, and when the beam is drawn here, there is a shortcut one for the graphical view for the object shrink. This is here. Shrink this, focus on this particular area. You can see the slab get meshed this horizontal line. So that is the default setting. The meshing is happening like that for this membrane type slab. Actually, it is a single entity, but during the analysis it get meshed and the load transfer will happen to the beam accordingly. So speaking of the load transfer, I would also like to show you it should be in the deformed shape to see that. Okay, load transfer, that's what we are interested in. You can go to the display, press undeformed shape. I go to the display, load assigns, loads to the frames. You want to see the tributary load coming to the frame from the slabs. So when you press the first one, which is dead, it will show what are the dead loads applied to the frame object. Set to the tributary will be different. So with the membrane type shell, you'll get this triangular and trapezoidal load distribution happening. You can see this better in live load, where there are wall loads on the beams. You can see the triangular and this trapezoidal. So this is available in the membrane type for beam slab systems. This is how the load transfer is. Here it will be like this. Shape, and under the display, we can switch to force stress diagrams. For example, the support reactions. You can read this for a combo or case, say dead alone. You can enable which are the components you want to have the output. So fixed, so you'll also have moments. So I'll enable moments as well, like this, or tabulated, and relate this, and read this, and right click, and just move the mouse and see this, or right click to see it in a form. And for the frames, say axial force, show values at controlling stations in the diagram. You can see instead of a 3D, you can switch to an elevation view. You can go to view, set elevation. Let's go for grid 2. Yes, I see the moments, dead load. Moment measure will be M33, minor will be shear measure will be in 2. Same goes for the live. You right click on particular member, then you'll get more details how the load transfer is happening. Then can scroll to read values at a particular location or specify it 2 meters. And you can also get the deflection value related to beam ends. You can switch to other absolute, etc. But this is showing the major components. You can switch to minor direction and then axial torsion about one axis. These are the outputs, and shell stresses, as of now, it's a membrane. It can have only the in plane, can get the forces, stresses, and strains. Typical finite element output in plane forces. So all of these graphical outputs you can get under the show tables in a tabular form. For example, you want to see, so you got 3 branches. One is model related, all the definitions, load patterns, material properties, section properties, etc. here. And you have analysis results. Let's say under the analysis, you want to see joint outputs such as reactions. You can select particular combos. So you get the ID in terms of story and label, or unique name. 2 ways you can refer to an object. You can see the forces for each type. For example, select only this object and go to display show table. Again, same table. So it will show only the selected objects output. It will be handy. And this can be exported to Excel. Can add more tables to this other outputs, total base reaction, etc. So design data, we haven't performed it, so it is available. You'll get the relevant tables here. That what is the base reaction for the total entire structure? I mean, total vertical load acting on the structure. Just for some quick checks, you can use this. Right. Let me quickly introduce you to the lateral loads. For linear static lateral loads, we will cover the response spectrum, time history, and other types in the next session. It's very simple. All you have to do is, it is completely automated in this program. All you have to do is to define the relevant parameters, the input parameters. So for example, I want to define seismic load. You have to specify and define the mass source first. There is a default mass source we use. So it is the self mass and additional mass. If I want to specify it as per, let's say, Indian code 1893, which is, then use the third option. This pattern will be enabled. Dead load 100%, live load, let's say 25%. So as 0.25. So by default, lateral masks are active. If you want to consider vertical, you can enable this. Right? And masks are lumped at the story levels for now. Be typical for most building systems. So that definition is the mass source. So whenever a mass is required for the analysis, it's a source. Now we are defining a load pattern. Let's assume this building is in zone 3, and you're going to define This is how you define a pattern. Write the name, specify the type seismic, self-weight 0, multiplier is 0, and you can specify code-based auto lateral load or keep it none in case you want to apply the loads manually using any of the joint load, line load, or shell load option. That is none. And IS 1893. We will discuss about the diaphragms in the next session, but for now we can keep it without diaphragm. Its uses will be discussed. This is EQY. Now for the EQX, can specify how this direction eccentricity to be considered. So I'm excluding the eccentricity. We need diaphragms for that, which will be discussed in the next session. So I'm giving X direction only. Zone 3, and the program calculated internally program will perform a model analysis, and it uses a particular direction. This is X direction. The maximum, from the model result, it will get the time period. But in typically we'll be using the user defined, where we will specify the formula given in the code. So calculate and give it like this. I'm giving 0.3 for the structure. You can specify other parameters, R, Z, importance factor, and site type, which is soil. And from bottom to top, it's the range, and you can specify that. Same definition goes to Y, but in Y direction. Let's say this is 0.7. That's all you'll have to do. You can go ahead and run the analysis. Just in case you're wondering what about the load cases, program would have already created those cases, the same name. You can simply go ahead and run the analysis. Go to the deformed shape. From the dead, I've switched to EQX. There you go. UX 11.5 mm. Formation, the roof level. This is about 12.3 mm EQY. And go to the combinations. You can see program automatically updates the combinations for the EQX and EQY cases as well, as per the Indian code selected. See moments for the lateral load case, gravity case, can switch to any combination with those outputs, right? So once this is lateral load is analysis performed, you get story response plots. Can make use of this to see what are the loads applied to the stories. You can see in a tabular form this specific case, or what is the maximum story displacement X, different levels, or story shears, drifts. Drifts. Check the drift limits as per the code. Story shears, base shear diagram, story stiffness to check the stiffness limits, etc. So this particular plot will help you in deciding those limiting requirements from the code. Once this is done, let's assume that the analysis results are fine. Can switch to the design part. So this time we are going to discuss only the concrete frame design. I'm going to perform this. Can select the code, relevant parameters. So for example, number of interaction curves and points for the PMM interaction surface. Then the eccentric moment, minimum eccentricity should be considered or not. Additional moment to be considered or not. P delta for seismic ductile design, beam column capacity ratio check to be performed or not. All of this. I'm setting it to the defaults. So combinations automatically generated will be automatically included. In case you have special combinations, it will be available here. You can select and add it to the left, sorry, to the right. Be included the design. Note the program will perform design for all the combinations, not for envelope. That's what recommended as well. Going to perform the design. The design output like this. So discussion on the design output, we will keep it for the next session. We are left with only 5 minutes. Get the detailed output of a particular section like this, or can get an envelope directly from here. Currently, all the members are passing in this analysis, so get to see the rebar output reported. In case of any failure, you will see O/S written, that is overstressed. Then that member can be investigated for the reason and rectified accordingly. For example, a column design will use this PMM interaction surface, and the maximum rebar reported from all the combination will be reported in the graphical window. It's what get highlighted here, and you get to see the details. It includes the calculation of effect length factors, additional moments, if any, minimum moment, initial moment, and the design moment from beam column capacity ratio or capacity design. All of are included in this design. So I will stop my presentation at this.